Yeah, thanks for the introduction. This is joint work with Karen, of course. Yes, so what is this about? This is my PhD project, which I started in October, and the first goal was to build a C-star algebra. Which we call O of E for reasons that will become clear later, from the following data. A compact metrizable space X could be locally compact, but for this talk I will assume it's compact. A partial automorphism. Theta on X. I will introduce what partial automorphisms are during the talk. And okay, maybe let's and a vector bundle. Curly V over X. And this construction should generalize cross products by the integers. So we will see later that if the vector bundle is a trivial line bundle, so it's just X times C, then we recover the usual cross product. Okay, partial cross product. Sorry. So if this is global, then it's the normal one, and if not, it's the partial one. Thanks. Yes, and once you have this construction, you can of course ask many questions. So, for example, how are properties of this data, the space, the partial automorphism, and the vector bundle reflected in properties of the algebra? So, for example, we would expect that that minimality of theta somehow related to simplicity of of the C-star algebra, just because it's a generalization of cross products, and this is how it is for cross products, right? And in this, for the same reason, we would expect that the covering dimension of the space is related to the nuclear dimension of the algebra. And we would also expect that theta invariant measures on X are related to tracial states. On the C-star algebra, because this is all of this holds for cross products. And then furthermore, you can, for example, ask, are there Kettner subalgebras? And if yes, what are the associated twisted groupoids? We will see that there is a Z grading. So you can look at this. And yeah, you can ask, how does it look like? In particular, how does the fixed point algebra look like? And of course, you can ask about the K-theory and so on. So these are the things I've been working on over the last couple of months, except for the K-theory, which I haven't looked at. But most of it is still work in progress. And therefore, today I will mostly talk about the construction itself. And then if I still have time, I will say something about the grading. Yeah, that's the plan for today. And why is this interesting? So the hope of the long-term question is, does this construction exhaust the Elliott invariant? Or put differently, can we construct all classifiable C-star algebras in this way? So we know that you can exhaust the Elliott invariant using twisted groupoid C-star algebras. That was shown by Xin Li. And yeah, maybe this is a different way to do this. Both. I will talk about that. Yeah, I will say a little bit about that later. Okay, but first, this is, so to say, like in the future still. Today, I want to talk about the construction, and for that, I need to talk about C-star correspondences and the Conditional algebras that are associated to them. Okay. So let A be a C-star algebra. Then we make the following definition, and I'm sure that almost all of you have seen this already, but I'm going to write it down anyways. So a right Hilbert A module. What is this? It is a right A module which we call curly E, together with a Sasquilinear map. Or actually, map. I mean, this is moment. From E times E to A. Yeah, so this is supposed to be a valued in a product. So we need to impose the following conditions. We want it to be linear in the second slot. 2 times A. And we want it to be anti-symmetric. and we want it to be positive definite. Yeah, for all psi, eta 1, eta 2 in E, and all A and A. Yeah, so it's really an A valued in a product, and then also this right A module should be complete. With respect to the norm. So this norm. So we take the inner product of psi with itself. That gives us an element in A. And so we can take its A norm, and then we take the square root. And that gives us a norm. And yeah, it should be complete with respect to this norm. So the most obvious example clearly is just a Hilbert space. But the example that is relevant for us is a different one. Let's look at the space of continuous sections. Space of continuous sections of V. So the notation in the introduction is fixed. So X will always be a compact factorizable space, and V will always be a vector bundle. And then we can look at the space of continuous sections of V, and that is a right Hilbert C of X module. So now I need to tell you what are right multiplication and what is the inner product. The right multiplication is given by just pointwise multiplication. So this product is the section that at each point is this vector multiplied with this complex number. And the inner product now I could write this down. Yeah, I mean, I can give you the formula if you want explicitly, but I'm just going to write pointwise inner product of sections. So what a section does is that in each fiber, it picks a vector, right? And so if we have two sections, then in each fiber, we have two vectors, and we can take the inner product of them and get a complex number. And so for each point of the space, we get a complex number, and that gives us a continuous function. So this is really C of X values. I know, I mean, it should be, so the difference is that a Hilbert bundle doesn't have to be locally trivializable, right? Is that the definition? Oh, but if it's finite dimensional, then you always have a... sorry, yeah, I should have said that, sorry. So for me, that's just like clear now because I've always worked with this case, but yes, okay. Fibers are finite dimensional, so I don't know how you write that. Rank of the vector bundle is still like yes. Good question. I'm not sure. I'm not sure. I mean, I guess there would be then different choices of an inner product for this. So just as you can choose different inner products on CFN, you could choose different ones. Yeah. I mean, but this comes with the local trivialization, right? So and maybe I should have written down the formula specifically. So if I remembered correctly, it's like you choose a local trivialization, UI, HI, let's say, where HI goes from, which way is it now? Like this into the vector bundle, right? Hope I'm getting this right. And so you choose a partition of unity subordinate to the UI, and then the inner. So this thing, if I insert sections here, this is equal to the sum over this, and then you take HI inverse of, I guess, yeah, this thing. Hope that makes sense. So basically, when you have a local trivialization, then this chooses the inner product for you, right? Like, because it tells you like what way you. So that should be continuous.
Yeah, I guess in T-squared is often because not locally trivial bundles, right? Which is semi-continuous.
Yeah. Right. Yes. Okay. Right. Sorry. Yeah. I mean, it should be somehow pointwise. Yes. Okay. Continue. Yeah. So this is this makes this into a right CFX Hilbert module. Okay. So now that's that. Now I want to introduce what a C-star correspondence is. For that, we need a little bit of notation. We denote by L of E the space of the C-star algebra of adjointable A linear operators. Yeah, so E is here a right Hilbert A module. Adjointable means there exists an adjoint with respect to this inner product, and then it's automatically bounded. The operator is automatically bounded. And just like for ordinary Hilbert spaces, we get an ideal sitting inside of L of E, which are the compact operators. So how do we define the compact operators? We take two elements of the Hilbert module, and we define the rank 1 operator, theta psi eta, in the following way. So this should do exactly what you would expect from a rank 1 operator. This. And then you define the compacts, to be the closed linear span of the rank 1 operators. Okay, and this is an ideal in L of E. Yes. And now we can define what a C-star correspondence is. A C-star correspondence over A is a right Hilbert A module E, where additionally we have a star homomorphism phi E from A into the adjointable A linear operator. So this is some kind of left multiplication, I guess, but it doesn't have to be compatible with the inner product. Yes. Okay, so now as an example, we can just take this example and upgrade it a little bit. So we take the right Hilbert C of X module that we were just looking at, the space of continuous sections of the vector bundle, and additionally we take a homomorphism on X. So that's basically a Z action, right? And then we can define this phi E, the structure map, by saying that we want so the structure map of F, what should it do? It should be right multiplication, but after composing with alpha. So yeah, it's exactly right multiplication, but first we have to compose with alpha. And of course, you have to show that this actually gives you a C-star correspondence, so that this is an adjointable operator, but it is. And yeah, so this is a C-star correspondence. The C-star correspondence was studied in a recent paper by Marzi and Karen and 5 other people. Adamo, Archie, Georgescu, Porro, Young, Strong, and Viola in 22. Yeah, and so the C-star correspondence, and then the C-star algebra constructed from this, which I'm going to introduce in a second. So now we have C-star correspondence, and we want to construct a C-star algebra. And as I have said several times now, this is maybe that's a good time to clean the board. This should generalize cross products by the integers. So the way you construct the reduced cross product is that you take a representation of the dynamical system, and then you define the cross product to be the C-star algebra generated by the image of this representation, right? And we want to do something similar here. So I guess this can go. So for that, we have to introduce representations of C-star correspondences. A representation of a C-star correspondence on some C-star algebra consists of a star homomorphism from A, which we call pi, from A to B, and a linear map. T from E to B, such that two things hold. First of all, we have a compatibility relation with the inner product. So the inner product of psi and eta, if we map it to B using pi, this is the same as mapping, as this expression. And then secondly, we want left multiplication, or the structure map to be preserved. So this is and from this, it already follows that also right multiplication is preserved, so we don't need to demand that separately. And if we have a representation of the C-star correspondence, then we can look at the C-star algebra that the images of pi and t generate, and that we call C-star pi t. That's the C-star subalgebra of B, generated by the images of pi and t. Okay, but now this is not quite enough. We need to demand something else. If you recall the construction of the cross product, there we look at covariant representations of the dynamical system, and we need this here too. So we need to introduce what covariance is, and for that, I need a little more of notation. So the construction as I present here is from a paper from Katsura in 2003, I think. And so the following ideal is sometimes also called Katsura's ideal. That is this thing. The pre-image of the compacts under the structure map intersected with the annihilator of the kernel of the structure map. So this is these are all A and A, such that the product with every element in the kernel is 0. Yeah, this is just a technical thing which will appear in a second. So this is an ideal of A. And now we define a star homomorphism. Or maybe it fits here. called psi t from the compacts of E to B in the following way. So it's enough to specify it on rank 1 operators because those generate the compacts, and on rank 1 operators it should map this map a rank 1 operator to this expression. Yeah, and that for all rank 1 operators, and then this uniquely specifies the star homomorphism on the compacts. And now we can finally say what covariance means. We say that the representation phi t is covariant. If it doesn't matter whether I map an element A into B using pi, or I first map it to an operator using the structure map, and then I use this psi t map into B. And of course, this only makes sense if this thing here is compact. Otherwise, psi t is not defined. So we only demand this for A in this ideal. Yes, so that's what covariance means. If you look at the special case of a cross product, you can see that this is exactly covariance for cross product. So if you take, I'll talk about that in a second, but if you take our example from earlier and then you let V be a trivial line bundle, then it's not too hard to see that everything boils down to the cross product construction, and covariance is exactly covariance for this representation of the dynamical system. Okay, so now again we want to construct a C-star algebra. So we want to take a special representation and define the C-star algebra to be this thing. But now what does it mean to be a special representation, right? So far, if I take different representations, I get different C-star algebras, possibly. So we need to define universality. So a covariant representation phi u tu is universal. If for all covariant representations phi t, there exists a surjective linear map rho from the C-star algebra generated by the universal representation to the C-star algebra generated by the other representation. Sorry for the bad spacing. Yeah. And then, of course, from this, it's immediately clear that if you have two universal representations, then they generate isomorphic C-star algebras. So now we can finally define the Cuntz-Pimsner algebra. Let PU/TU be a covariant universal representation. Then the Cuntz-Pimsner algebra of E is defined to be, as I already said, just the C-star algebra generated by this representation. And that is unique because of this universality. Now, of course, at this point, it is not clear whether a universal representation exists. So you have to show that by constructing it explicitly. But yeah, you can do that, and then you see that this actually is well defined. Okay, so now examples again. Now I'm going to stick to this example. As I already said several times, and now I'm going to write it down, if you take V to be the trivial line bundle, so V is just X times C, and again, alpha is a homomorphism. Sorry. And the C star correspondence is this one. Then the Conditional algebra is isomorphic to the cross product. Yes, so that's when the vector bundle is trivial and a line bundle, and if the vector bundle is not trivial or it's higher rank, then you get different things. So for example, if your space is trivial, it's just a point, and then of course the homomorphism has to be trivial, and of course the vector bundle also has to be trivial, but it's higher rank. So this is the point times C to the n. Then the Cuntz-Pimsner algebra is isomorphic to the Kuntz algebra of order n. And that's what I meant earlier with we can also construct purely infinite things. So that's what you get if the vector bundle is higher rank. Yes. Okay. So now we are almost in the setting that I advertised in the introduction. So we have if we have a compact metrizable space and we have a vector bundle over the space and we have a Z action, a homomorphism, then we get a C-star algebra that generalizes the cross product. But what I said there was that we want to take a partial automorphism and not a global one. So I need to introduce partial automorphisms. When did I start exactly? 50 or 55? I don't know. Oh, at 5. Okay. A partial automorphism. Right, sorry. We first have to choose two open sets. Maybe I write that. Where do I write that? So we choose two open subsets of the space, and then the partial automorphism is simply a homeomorphism theta from U to V. So yeah, it doesn't operate on all of the space. It just maps some open subset to some other open subset. And just like we can interpret a usual global homomorphism as a Z action, we also want to interpret this as a Z action. But it's not immediately clear how this should work, because for the global homomorphism, you can just take the powers But here we cannot just take powers because it doesn't have to be well defined. So if this is the picture, if this is the space, and then we have two open subsets U and V, and theta maps U to V. If we take a point in U and we map it to V, then we don't know whether we can apply theta again. So we don't know whether theta squared will be well defined. This is only the case if this point that we map to is again in U. So we have to deal with domains where theta to the n maps d minus n to dn. The dn's are the domains, they're open subsets of X. And explicitly, we have that d0 is all of X by definition. D minus 1 is U, d1 is V. And by what I just said, d minus 2 is theta theta inverse of the intersection U times V, because those are the points where you can apply theta twice, where that get mapped into the intersection by theta. And accordingly, D2 would be theta of U intersected V, and so on. And it's clear that these domains get smaller and smaller. So you have a chain of domains. Minus 2 is contained in D minus 1. It's contained in D0, obviously, which is X. And then this contains D1 and so on. Okay. So now I should clean the board again. Okay. Yes, so what are examples of partial automorphisms? Of course, a very boring example would be, or maybe I continue here. A very boring example would be just a global one, obviously, where the domains are everything. Second example is that we can restrict global homeomorphisms. So if we have a global one, and we can just choose some open subset of X, and then we define V to be alpha of U, then we get a partial automorphism from U to V in the obvious way. So every global homomorphism gives rise to partial automorphisms by just choosing some open subset. And now to give a third example, which doesn't directly come from a global action. Take x to be the natural numbers. I don't know how deep I can write, so you can still read this. I know the display is annoying. Like this. And u is the natural numbers without 1. V is everything. And the partial automorphism is the left shift. So every natural number, what we do is we subtract 1, and we can do that for all natural numbers except 1 itself, because then we would leave the natural numbers. Okay, and now I can finally go to the setting that I outlined in the introduction. So now we want to construct a C-star correspondence out of a partial automorphism. So we want to take the example from before, the C-star correspondence, and then make it slightly more general. How do we do that? Let theta from U to V be a partial automorphism. On X, and now, of course, we want to do the same thing as before. So we want to define the structure map by multiplying from the right with F composed with the partial automorphism, but we run into trouble because of the domains. So we take E to be all continuous sections which vanish outside of U. This is the C-star correspondence. With so right multiplication and the inner product are as before. That doesn't change, but now the structure map is given by the following. So what we want to do is take F to the left side and to the right hand side and compose it with theta, but we can't just do that because of domain issues, so we need to be a bit more careful. This is xi of x times F composed with theta only for x and u, and otherwise it's just 0. This is well defined because we chose our sections to vanish outside of U. So this will still be a section which vanishes outside of U, and it will be continuous. Okay, so of course, again, you have to prove that this is indeed a C-star correspondence, but you can do that. And then, I'm sorry. Then for new for V, again the trivial line bundle, we get the partial cross product as Masi said in the beginning. So the Conditional algebra of the C-star correspondence is isomorphic to the partial cross product. That was shown by Muli and Solel. Yeah. in 89. So people have been looking at these things for quite a while now, but they only considered this particular case and showed it's isomorphic to the partial cross product. They did not look at more general vector boundaries. Okay, I have 10 minutes left, so I would maybe quickly talk about grading. So yeah, so now this was the construction. We are here now basically. So we have this. We constructed the C-star algebra out of this data, and we know that it generalizes the cross product by the integers. Now quickly about grading. So this actually works in general for any C-star correspondence. We have a gauge action, which is a strongly continuous action gamma from the torus on our Cuntz-Pimsner algebra. Sorry. Which is defined in the following way. So for elements in A, it just does nothing. So here I identify an element A with its image in the Cuntz-Pimsner algebra without really saying it. And I will do the same for elements of the C-star correspondence. So it acts on elements of the C-star correspondence by multiplying them with Z for all psi in E. And this gives you a grading over the dual group of the torus, which are the integers. So this gives us a Z grading. So this the Cuntz-Pimsner algebra can be written as a direct sum of these spectral subspaces where En bar is just the space, or the space of all elements which behave like this under the gauge action. They pick up a factor of Z to the N. And now we can explicitly write down how this looks like basically. So the just En without the closure, that is the linear span of the following of elements of the following form. We take psi1, psi L plus N, and then eta L star, eta 1 star for psi1 blah 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 in E. So what this says is just we take elements of this form where we have N more things without a star than things with a star. Yeah, so this is how the subspaces look like. And this is a topological grading in the sense of Excel. Which means that this forms a Fell bundle. And you have a conditional expectation. From the Cuntz-Pimsner algebra to the fixed point algebra. And now, how does this help us in our example? So for usual cross cross products, so for the trivial line bundle case, it's clear. So okay, just write it down. This is then cross product. We know all of this. So the conditional expectation would just map an element of this to F0, right? Where U is the unitary that generates the cross product. And oh, sorry, I should have written that first. This fixed point algebra is just C of X. And that generalizes to the line bundle case. So even if this is not trivial, so for a line bundle, you have that this is the C of X. And but this doesn't work anymore for the higher rank case. So for example, if like before, we take the setting where we get the Cuntz algebra. Then we know that this fixed point algebra will be the UHF algebra of type, you write this, of type n infinity, where n is the rank of the vector bundle. And of course, yeah, this is not C of X. So, and this is a little problem because I'm running out of space again. This is a little problem because for cross products, you do a lot of things. So for a lot of things, you use that this fixed point algebra is easy to understand. So often you go from the cross product to the fixed point algebra using the conditional expectation. And then you use that this is something you can understand. So for example, if you want to investigate the ideal structure, then you can show that ideals here are exactly ideals in here which are invariant under the action, and then you get that this corresponds to invariant subsets of X. And similarly for states here, you can use phi to show that they come from invariant measures here. So a lot of things work with this, like going to the fixed point algebra. And this still works for line bundles, but it doesn't work for higher rank bundles anymore because this is not abelian. It's not easy to understand. So that's one thing that we've been looking at, is to understand this fixed point algebra for also higher rank things. I mean, it works, I think. So it turns out this is a C of X algebra, and yeah, fibers isomorphic to the UHF algebra, but yeah. Anyway, so I think that's all I wanted to say. So thanks for your attention.
Okay, thanks for the talk. Are there any questions? So, do you know when C of X is a Cartan subalgebra? You mentioned this.
Yes, very. Thanks for the question. So it's the same as for cross products, that it's, I hope I remember it correctly, but it's if it is topologically free, then for the cross product it's a Cartan subalgebra, right? And that holds still for this line bundle case. But of course, that's another point. So here, of course, it's not abelian, so it can't be Cartan.
And can you realize then some Kirchberg algebras with a Cartan?
I don't know. I'm sorry. So yeah, I sorry, maybe I don't have the background to understand that question.
Yeah, and I mean this situation with the point seems to be degenerate because the action is, well, very non-free, right? So I mean, which C-star algebras do you get from free actions of the integers?
You mean in the higher rank case?
Mhm.
I don't know, but I still, it's a good point, but still I think this it shouldn't be a Canton because it would still be non-abelian, I guess. So it's
But are they stably finite? Do they have a trace?
again, thanks for the question. So so basically when it comes to these three things here, okay, no, sorry. The answer is yes if it's a line bundle. If it is higher rank, then it doesn't have any. No, then it doesn't have any traces. If it's so if in all points the rank of the vector bundle is greater than 1, then it doesn't have any traces. If it's just if it's greater than 1 on some connected component of the space and one on the others, then the trace is not faithful. Then it has to vanish on sections which are supported on this connected component. And yeah, but so for the line bundle case, basically everything works in the same way as for cross products. But then for the higher end case, it's yeah, you don't have traces. That's a good question. I think yes. I think I proved that at some point, but I have to go back and check if I actually did. Not sure. Yes. For the line bundle. That's Karen's hope, I guess. I don't know. That's how I understood the project so far, that's like the goal that we're working towards.
To get stably finite one. I mean, if I understand it correctly, it has to be a line bundle. But then is it then a twisted cross product?
Twisted, that's the stuff of coast cycles, right? Like you're twisted by, or what's a twisted cross product?
Well, twisted with the line bundle instead of the trivial.
Yes.
And is there really a hope that could realize all of the
I mean, apparently, I guess. I mean, for partial actions, that's I think why you want partial actions instead of global ones, because then you get more than. Yeah. So, for example, the Yang-Su algebra and AF algebras can be realized as partial cross products, right? Which cannot be realized as global cross products.
Yeah, it's totally.
Was it?